What's up, everybody? Welcome to the 14th lecture of Contemporary Math, and today we're going to be talking about correlation. Before we get into too much detail about correlation, let's first talk about what correlation looks like and what a scatter plot is. We'll start off with a scatter plot. A scatter plot is really just exactly what it sounds like. You take points, you put it onto a graph where the x value of a point represents one set of data and the y value represents another set of data. So we might have, for example, the height of a flower and the number of petals on that flower. We can represent the number of petals numerically, and we can represent the height numerically. So because of that, we can say, all right, the x value represents the height and the y value represents the number of petals. So get a nice scatter plot. And when we plot that, we might notice that the plots, they kind of congregate in very particular ways. This congregation can lead us to being able to tell whether or not things are strongly correlated or not. For example, in this particular scatter plot, whatever the x value represents and whatever the y value represents, it looks like there's a really strong positive correlation here. And that's because they're really tightly grouped, the points, the scatter plots, really tightly grouped around this line. Now, in this case, it's not a weak correlation, but it's not a strong correlation by any means. It is definitely a positive correlation, just a meh correlation. In the case of this middle plot, though, no correlation, none, nada, zip, zip, zilch, zero. There is no real congregation of points that allows us to say, yeah, these things are tightly related. The way this changes has something to do with the way this changes. Okay. Well, in this next case, it's a fairly moderate case of negative correlation. And those things are definitely related. How strongly? Meh. They're not weak, but they're not strong either. And then the final case, we have perfect correlation. All the points are tightly bound to that singular line. Now notice when I'm talking about correlation, I'm talking about this line, right? I'm somehow saying there's this line and these things are grouped together. They're clustered around it. But that line's not always there, is it? In fact, when we start writing down the data and making these graphs, it's often the case that we have no clue if this line even exists. None. No clue. But we can still look at the data and we can still see, yeah, there's probably a line in here somewhere that the data clusters around fairly tight. So, okay, how do we measure correlation? That's the next obvious question, right? Because if we're going to talk about correlation, we probably want to measure it. And if we're going to talk about these lines, probably going to want a way to calculate those. But they're going to need something to do with correlation. So let's get into it. Let's look at that. Okay, so let's say we're given a bunch of data. And that data happens to be the collection of respondents, A through J, the number of years they've been teaching, and the score they make on a test judging their level of prejudice. So we get this data, we're like, all right, let's put it on a graph to get an idea of what's happening. Let's make a scatter plot. So we put it together into a scatter plot where the number of years teaching is our x value, and the score on the exam that they took, that's the y value. We sit here and we're like, well, the data, it has this generally negative slope. So if it's correlated, it's going to be a negative correlation. And I do kind of, looking at this, get the impression of a line existing here, right? Like, it does look like there's something, there's some sort of cluster there. Okay, so I expect a relatively decent R value, and for that R value to be negative. How do I find that R value? So this is the point, the part of the lecture where I ask, please don't have me murdered, but the equation to find this does look bad. It's not going to be that bad though. To find the R value of a scattered plot, what we do, we take the number of values, so the number of data points, multiply it by the sum of our two data sets, our X and our Y value together, right? So we're multiplying X and Y together, taking the sum of that. Then we're subtracting the sum of the X values times the sum of the Y values. After we do that, that's going to be our denominator. After we do that, we're going to take the square root of n times the sum of x squared minus the sum of x, that quantity, squared, times the quantity n times the sum of y squared minus the sum of y, that quantity squared. Like I said, I know that sounded bad. Promise it's not though. The easiest way to tackle all of this, to keep everything straight as far as making sure you're not going to make any mistakes in the calculation, is to make a table. Start off by making a table of x and y, have a column for x times y, a column for x squared, and a column for y squared. Go through and write out all the values for x and y, then all the values for x times y, then all the values for x squared, and all the values for y squared. Once that's done, you're going to want to take and add all of these values in each row together and put them in their corresponding columns. That way, when you come back to putting everything into the equation, you don't make any mistakes with jumbling up numbers. Yeah, so, having said that, let's move on. Well, actually, before we move on, just showed how to find that R value, but what about the line? That sort of imaginary line that we sense to be here. How do we calculate that? I'm glad you asked, because that's where we're going next. So as you can see, I went ahead and calculated a couple things here. First, I went ahead and calculated what the R value is. And we had already figured that it was going to be pretty high, right? Like it was going to be a strong correlation, but negative. And it was. It came out to be negative 0.92. So now's the time where you're probably looking at that saying, why is that strong though? What it means for a correlation to be strong, for an R value to mean a strong correlation. What it means is that you're further away from 0 and closer to either -1 or 1. The further you get from 0, the stronger your correlation becomes. In the case that you're moving in the negative direction, that implies you're going to have a negative slope represented by that line of regression, that line of connection that I was sort of talking about before. If, on the other hand, your R value is positive, well, that means your slope's going to be positive. So having said that, I went ahead and also calculated what the equation for that line here would be. And that equation comes out to be y equal to negative 0.39 times x minus 11.05. How did I find that? I'm glad you asked. I found it. Please don't, I know after that last equation you probably want to already have me murdered. Please, don't call a hit out on me. That would really make my mom sad, okay? Please. I know these look bad, but I promise they're not, guys. So, the way I found the equation for this line is by first calculating the slope of this line. And that slope, m, is equal to n times the sum of x times y minus the sum of x times the sum of y, all of that then divided by the sum of x squared, that quantity multiplied by n, minus the sum of x, that quantity squared. So that's m. B, the intercept, that's going to be the sum of y minus m times the sum of x, all of that divided by n. And then we put it together in a nice little equation. This equation here, all this put together, represents or provides us with the equation for this line. This line that I keep alluding to. And what this line is the regression line, or the line of best fit. It's the line that all of your data is on average closest to. There's no other line that better fits your data. That's all this line really is. It's saying if we were to hold all of the points roughly equal distance away from, or minimize the distance from your line to all of your points, this is the line that does that. And that's why it's called the best fit line, or the regression line. Before I let y'all go, I really quickly wanted to ask that y'all read page 827 and 828, the little section on the level of significance of R, your coefficient, your correlation coefficient. I also want to ask that y'all look over all this material one last time in the book itself. There are a lot of examples that I just simply can't go over on the board here. And a lot of this material I personally think is more easily understood through conversation. However, since we can't have those conversations, there's going to be some things that the book explains much better than what I am able to at the board. So with that in mind, I would ask that y'all go through this chapter 12 in the book. And again, just to look over that last little bit about the level of significance of your R value. Having said that, have a good one, guys. If you have any questions, by all means, please shoot me an email. In the meantime, enjoy your 4th of July.